Imagine you are moving thousands of tons of volatile boiling liquid across the ocean, and the temperature of this liquid is a staggering minus 163 degrees Celsius. So what is the main thing standing between that catastrophic energy and the open sea?
I mean, you naturally picture massive, impenetrable walls of solid iron.
Exactly. But the reality is actually a piece of corrugated stainless steel that is only 1.2 millimeters thick. And backing up that paper-thin steel is just, well, a layer of foam.
Yeah, the contrast between the sheer scale of the energy being transported and the fragility of the containment system is just insane. It's one of the most intense balancing acts in modern marine engineering. We literally rely on millimeter-thick membranes to hold back an ocean of freezing volatile mass.
Welcome to this deep dive. Today we're unpacking a really fascinating source titled Mark III LNG Systems, Why the Failsafe Fails. And our mission here is to understand how massive liquid natural gas carriers can be brought to their knees by microscopic cracks. We're exploring the specific mechanical mystery, which is why the secondary backup safety layer is secretly failing while the primary steel layer remains perfectly intact.
Which is wild. And we're really looking at a concept that engineers call structural criticality.
Structural criticality.
Yeah, because the intuitive assumption is that a structure's survival depends on the sheer thickness of its primary armor, right? Like thicker is better. But structural criticality completely flips that. It dictates that the integrity of the entire ship relies entirely on the hidden microscopic interactions between distinctly different materials layered on top of each other.
Okay, let's unpack this multi-layered sandwich because we need to visualize the physical structure of the Mark III system to actually understand how a failsafe fails first.
Go for it.
So the inner layer, the one physically touching the liquid natural gas, is the primary barrier. That's the thin 1.2 millimeter corrugated stainless steel.
Right.
Immediately behind that steel is a thick block of reinforced polyurethane foam, or RPUF. Then behind that foam is the secondary barrier. This is the failsafe, which is a very thin composite made of aluminum and glass cloth. And then finally, there's another layer of foam before you reach the actual steel hull of the ship.
Yeah, and the foundational engineering concept to grasp about this whole layout is the idea of a supported membrane.
Okay, supported membrane.
Right, because those thin layers of steel and aluminum, they're not structural beams. They possess virtually no rigidity on their own. Like they cannot hold back the weight of thousands of tons of LNG.
Yeah, 1.2 millimeters isn't holding back an ocean.
Exactly. They rely 100% on the polyurethane foam behind them to take the physical load.
I think of it kind of like putting thin wallpaper over drywall. The steel and the aluminum are just the wallpaper. If the drywall, which is the foam behind it, is solid, you can lean on that wall all day. The wallpaper simply transfers your weight into the solid drywall.
That's a great way to picture it.
But if there's a hole in the drywall, right, like a void in the foam, and you push on the wallpaper over that void, the wallpaper pops. It tears. The membrane is suddenly forced to carry the load across an empty gap all by itself, and it just isn't built for that kind of tension.
Right. And engineers actually refer to that exact situation as a local lack of support. So a microscopic gap created during manufacturing, or even a localized area where the foam is compressed, it creates this critical vulnerability. The membrane suddenly has to act as a structural bridge rather than just a supported skin.
Okay, but let me push back on the mechanics of that failure, though.
Okay.
Because our sources indicate that the hidden secondary backup layer, the aluminum and glass cloth, is what fails first, while the primary steel layer right in front of it is totally fine. If the primary steel is taking all the pressure from the liquid and transferring it through the foam, how is the hidden layer further back breaking while the front layer survives? I mean, the primary layer is the one taking the beating, isn't it?
It seems like it should be, yeah. But the researchers at the Ryzen National Laboratory investigated this counterintuitive puzzle. And the answer lies in a phenomenon called buckling-driven delamination.
Buckling-driven delamination.
Yeah. So the secondary aluminum membrane is bonded tightly to the foam. When the system undergoes massive thermal shifts, the aluminum might want to shrink or expand at a different rate than the foam.
Okay.
Because it's trapped, the aluminum buckles. It literally lifts off the foam, tearing the chemical bond and creating a tiny blister in the secondary layer.
Oh, wow. So it's kind of like trying to shove a large rug into a small room. The edges are pinned down so it just bunches up in the middle.
Exactly.
But wait, if there are thousands of tons of liquid pressing down on the primary steel, wouldn't that massive external pressure just flatten the blister back out? Like a giant foot stepping on the bunched up rug?
You would think so, but the physics of that external pressure are actually much more sinister. The pressure pushing down through the layers doesn't flatten the blister smoothly.
It doesn't.
No. It presses down on the flat areas around the blister, which ironically causes the raised edges of the blister to flex.
Ah, I see.
As the ship moves and the fluid pressure constantly fluctuates up and down, those edges are flexed back and forth over and over again. It's identical to bending a paperclip back and forth until the metal just suffers fatigue and snaps. The pressure that intuitively should hold the aluminum flat is actually driving the fatigue crack.
That shifts the perspective entirely. We're talking about physical pressure from the liquid, but there is an invisible war happening inside this wall before the ship even moves an inch.
Absolutely.
The extreme cold is driving the failure. I mean, we're dealing with minus 163 degrees Celsius.
Yeah, thermal stress is arguably the most destructive force in the entire system, because every single material in that containment sandwich reacts differently to the cold, which is governed by its thermal expansion coefficient, or TEC. When engineers pump that freezing LNG into the tank during the initial cooldown phase, the stainless steel shrinks by a specific amount. The polyurethane foam shrinks by a completely different amount, and the aluminum composite shrinks at its own unique rate.
And because they are chemically bonded together into a single block, they can't shrink independently. They just start violently pulling on each other. It's like wearing a heavy wool sweater that's been tightly stitched to a silk shirt. You jump into an icy lake, the wool shrinks dramatically, the silk doesn't, and suddenly the seams are ripping apart simply because the materials are forced to occupy the same space while behaving differently.
That's a perfect analogy. And the consequence of that mismatch is the creation of permanent residual stresses. Immense tension is locked into the material at a molecular level.
You're locked in.
Yeah, the foam is being sheared and stretched internally, just sitting in the port. So a significant portion of its structural strength is consumed merely existing at minus 163 degrees.
Wow.
Which leaves less strength available to handle the physical impact of the ocean waves.
But wait, if engineers know these materials inherently fight each other in the cold and are, pulling each other apart from the inside, how does the foam actually survive that initial freezing shock without just shattering into pieces the moment the liquid hits it?
That is a great question.
Oh.
The survival of the system hinges on the unique material properties of the RPUF foam. It's highly strain rate dependent.
Strain rate dependent.
Yeah. Its physical stiffness and brittleness change not just based on the temperature, but on the speed at which a load or temperature change is applied.
Okay.
If operators cool the tank down over a long, carefully controlled period, the foam remains relatively compliant. It has the physical time to slowly stretch, deform, and accommodate the pulling forces from the steel and aluminum.
But if you cool it too fast, or if it takes a sudden, violent physical impact while it's already at that extreme temperature, it loses that compliance. It stops acting like a sponge and starts acting like brittle glass.
Exactly. The material essentially forgets how to flex. The internal structure locks up, and instead of absorbing energy through deformation, the cell walls of the foam simply snap.
Man, that sets up a terrifying baseline. Before the ship even leaves the dock, the walls are internally stressed to their absolute limits, locked in this frozen, glass-like tug of war.
Yep.
And now the ship enters the open ocean, introducing millions of gallons of liquid violently shifting around in a storm.
And the industry term for this fluid motion is sloshing. But the dynamics inside an LNG tank go far beyond the standard fluid mechanics of just, a water tank.
Right, because the scales.
Scale and the physics. When thousands of tons of LNG slam into the containment wall, the impact is hydroelastic.
Hydroelastic.
Yeah, the sheer force of the liquid physically deforms the thin steel wall and the foam behind it. And that structural deformation instantly alters the geometry of the tank, which in turn immediately changes how the fluid flows and how the pressure is distributed back into the wall.
So they interact with each other.
Exactly. The liquid and the containment system stop acting as two separate entities and become a single, coupled, vibrating unit.
And it's not just a clean, solid wall of liquid hitting the side either. As the LNG sloshes back and forth across this massive tank, the churning liquid traps natural gas vapor. It creates a highly aerated, frothy mixture at the impact zone.
Right.
Now, my initial thought reading the sources was that those bubbles would act as tiny shock absorbers, compressing to cushion the blow against the wall.
And it makes sense you'd think that. But while the bubbles do compress, their presence creates an absolute nightmare for engineers trying to model these impacts using computational fluid dynamics, or CFD.
Why is that?
Because the introduction of compressible gas bubbles into an incompressible liquid radically alters the speed of sound within that fluid mixture.
Oh, wow. So if the bubbles are compressing, the density of the fluid is constantly changing, like millisecond by millisecond. That must completely throw off how pressure waves travel through the liquid.
It makes predicting pressure spikes incredibly difficult. Engineers use something called the Wagner approximation to map these impacts.
Okay, the Wagner approximation.
Yeah, imagine the exact millisecond the wave of liquid touches the wall. The area of physical contact, the wetted area, starts expanding outward from the initial point of impact.
Okay, I'm picturing it.
If that wetted area expands faster than the fluid itself can physically move out of the way, the pressure has no physical avenue to dissipate.
It's like slapping the surface of a pool with a completely flat hand.
Yes.
The air is trapped, the water can't escape sideways fast enough to make room for your hand, and you get a massive, painful pressure spike.
Exactly. Now scale that up to a massive ocean swell of liquid natural gas. When the wetted area expands faster than the escape velocity of the fluid, you generate a highly localized, instantaneous acoustic shock wave.
That sounds destructive.
It is. In modeling, this appears as a triangular impulse response function. It's a sharp, violent spike in pressure that lasts for only milliseconds, but carries immense destructive force. And because the trapped gas bubbles constantly change the speed of sound and the compressibility of the fluid, CFD models cannot accurately predict when or where that critical threshold will be crossed. The location of the shock wave becomes essentially random.
Okay, so let me get this straight. We have an unpredictable acoustic shock wave hammering a delicate glass-like foam sandwich that is already tearing itself apart from thermal stress.
Basically, yes.
You obviously can't build giant structural steel baffles inside the tank to break up the waves because driving steel beams through the floor would ruin the continuous thermal insulation. The heat would leak straight into the tank. So engineers have to find a way to calm the liquid without touching the walls.
Right. The proposed solutions require altering the behavior of the fluid itself, rather than trying to infinitely reinforce the walls.
And the sources outline a remarkably creative testing phase for something called eccentric foam floaters, or EFFs.
Yeah, these are fascinating.
They are essentially thousands of giant, heavily engineered bath toys deployed directly into the tank, just floating on the surface of the LNG.
Giant high-tech bath toys is a pretty accurate way to describe them. And the key engineering element of those floaters is the eccentricity of their design. Their center of mass is intentionally placed drastically off-center.
Which is brilliant because when a massive wave starts to build in the tank, these floaters don't just passively bob up and down on the surface. Because of that mass asymmetry, the movement of the wave forces them to wobble wildly, spin frantically, and just grind against one another.
Exactly.
They actively convert the dangerous building kinetic energy of the sloshing wave into harmless heat and friction through their own erratic movement. They rob the wave of its destructive power before it ever reaches the containment wall.
It is a masterclass in passive mitigation. You literally neutralize the hydroelastic threat using the fluid's own momentum against it.
But until those eccentric floaters are universally deployed, the global fleet relies on the integrity of that 1.2 millimeter sheet of steel and the foam behind it.
That's right.
And we know we can't completely eliminate the thermal pulling, and we can't perfectly predict the acoustic shock waves. So what happens when these hidden vulnerabilities align?
Well, the result is a cascading failure. Imagine the secondary barrier, the hidden failsafe, develops a fatigue crack from that buckling delamination we discussed earlier.
Okay.
It's buried deep inside the wall, so it goes unnoticed. Months later, the primary stainless steel barrier develops a microscopic fracture from a violent, aerated sloshing impact. The minus 163-degree liquid natural gas now has the direct path through the primary steel, through the saturated foam, through the cracked secondary barrier, straight to the ship's actual outer hull.
And the outer hull is constructed from standard carbon steel, not the specialized stainless steel used for the primary membrane.
Exactly. Carbon steel possesses a ductile to brittle transition temperature that is well above minus 163 degrees.
Meaning?
The moment the cryogenic liquid makes contact with the carbon steel hull, the molecular structure of the steel changes. It loses all of its elasticity and flexibility. It effectively turns into glass.
Oh my God. The hull is suddenly bearing the immense structural load of the ship and the cargo while possessing the structural properties of a teacup.
Yes.
The next ocean swell that hits the outside of the ship, or even the intense vibration from the ship's own massive engines, could cause the entire hull to shatter, instantly splitting the vessel apart.
And the catastrophic nature of that specific failure mode is why the International Gas Carrier Code, the IGC code, imposes such rigid safety mandates. The regulations dictate that if the primary stainless steel barrier fails entirely, the secondary backup barrier must be mathematically proven to contain the cryogenic liquid for a minimum of 15 days.
15 days, just to give the crew time to limp the damaged vessel to a safe port and offload the volatile cargo.
Right.
But relying on a 1 millimeter thick layer of aluminum and glass cloth to hold back an ocean of boiling liquid for 2 weeks while traversing the open sea is, it's a harrowing reality.
It really is.
We spend a lot of time analyzing high-minded physics here, right? Thermal expansion coefficients, acoustic shock waves, hydroelasticity. But the sources highlight a deeply human element to these failures. Sometimes the trigger isn't a complex fluid dynamics anomaly. Sometimes it's just a worker dropping a wrench.
Ah, yeah. The concept of the latent defect. The human error embedded in the construction phase that remains dormant for years.
Right. Researchers conducted a study using a gun-type impact machine to fire bolts, heavy hand tools, and equipment directly at a full-scale physical model of the Mark III system to simulate construction accidents. And they found that if a worker drops a heavy wrench from scaffolding high up in the tank, it strikes that thin primary stainless steel. Now, the steel is incredibly tough and ductile. It absorbs the blow, perhaps forming a shallow dent, but it does not puncture.
Oh, it's fine.
Exactly. To the naked eye of a visual inspector, the membrane looks completely intact.
And that visual inspection creates a false sense of security because the physical mechanism of the damage occurs beneath the surface. The kinetic force of that heavy wrench doesn't dissipate in the steel.
Where does it go?
The steel transfers the shockwave straight through the metal and directly into the RPUF foam directly below it.
Oh. And the foam is crushed instantly by the blunt force impact. It permanently compresses, creating a localized void, a hidden cave right beneath the primary steel.
Exactly.
The force might even be severe enough to violently delaminate the secondary barrier further down the sandwich, ripping the chemical bond apart right then and there. And no one knows it happened.
This is the physical embodiment of the Swiss cheese model of risk management.
Right, the Swiss cheese model.
Yeah. A complex system has multiple layers of defense, but every layer has microscopic holes. The dropped wrench creates a physical hole in the support layer during construction in a dry dock. The thermal expansion mismatch creates a stress hole in the material integrity layer during the initial cool down. The aerated sloshing wave creates a massive, unpredictable pressure spike during a winter storm. An error made 5 years ago by a tired worker on a Tuesday afternoon silently waits in the dark for the exact right thermal and ocean conditions to perfectly align. When those holes line up, the fail-safe fails.
So how do engineers actively manage to